Hi, everybody. Today's talk is going to be on the Hadoop Distributed File System. I do not work for Bolt. I'm a friend of Bolt, and they've been kind enough to let me in the building tonight with my PowerPoint. My name is Mark Litwintschik. I'm a big data consultant. I do work with airlines, investment banks, global restaurant chains, major advertisers, supermarket chains. I did a stint at Google in 2014. I run a big data tech blog at marksblog.com. It is. I'm not yelling loud enough into it. Can everybody hear me, first of all? Yeah? Everyone knows who I am? That's what I look like with a tie on. So on my blog, I'm most well known for the 1.1 billion taxi rides benchmark. I've taken a data set of 1.1 billion records of taxi rides that were conducted in New York City over the space of 6 years, and I've run it on different software and hardware configurations. With a lot of this software, there is no one hardware platform that would be identical across all of them. But by and large, I can show what the different combinations will result in query speeds. So if I start at the bottom here, got Elasticsearch down here where running one of the 4 queries, it takes about 8.1 seconds. Then you get Amazon Athena, Presto, a lot of the Hadoop stuff's in here. As you get up here, you get to ClickHouse. So that came out of Yandex. Very fast analytical data store. KDB, so if you wanted to, it's used a lot with people who connect to the NASDAQ trading bus to monitor 1 to 3 million messages a second. It's very fast software. It's also quite expensive. MapD runs on GPUs, obviously super quick. The fastest I've been ever able to query this data set was with a 5-node cluster in IBM's headquarters in New York State using Brightlight DB. And so with that, we were actually under 5 milliseconds of looking at 1.1 billion records. The only downside is hardware costs $250,000. So I got started with HDFS back in 2010. I'd spent about 8 years before that building websites and sending out huge email campaigns, and you generate a lot of data doing that and trying to analyze it using SQL Server or MySQL or Postgres. You get to billions of records and then it becomes a bit of a joke. Cloudera had a sandbox to make it easy to install Hadoop. And I got that working on my laptop. It took me about 2 years until I could actually get someone to pay me to actually work on Hadoop. And even since then, I've been doing nothing but learning about it. The big thing about Hadoop and HDFS, it's free of charge, it's open source, it's developed in the wide open. It runs on super cheap hardware. It can store your largest data sets, but most importantly, it doesn't need to be large data. The same primitives work on small amounts of data as well too. I'm importing Excel sheets onto HDFS clusters and using the same APIs that deal with petabytes of data. I'm also dealing with kilobytes of data. I might not have the super high, super low latency that you expect of some of these other data stores, but my customers only have to worry about 2 or 3 different APIs, not 20 or 30. This is Michael Stonebraker. He invented Postgres, yeah? And he's also the author of a paper titled One Size Fits All, an idea whose time has come and gone. And the key behind this is that every database has a reason to exist. It's just trade-offs that you would have when you're trying to integrate it into your organization. And he makes an important point. If you can make your database very application specific, you can get 1 or 2 orders of magnitude of more performance out of it than you would have otherwise. So when you are thinking about like which data stores to look at, do keep an open mind. There's a lot out there. The other question is on how do you measure speed? Yeah, and often when you're measuring speed, it's like, well, what's the application? This race took place in Turkey last year. There was a Formula 1 car, there was a fighter jet, there was a private jet, there was a bike. And if you wanted to know which one was the fastest, it was dependent on how long the race was for. If it was only a 400-meter race, the bike would win. If it was a kilometer long, the Formula 1 car would win. You get to 10 kilometers, the fighter jet would win. But if it was 1,000 kilometers that you needed to travel, that fighter jet would have to refuel like 4 or 5 times. So you just end up with a private jet being the fastest. Adam Drake, I'm sure he's a really nice guy. He does retweet some of my tweets. But unfortunately, he did write a blog post called "The Command Line Tools Can Be 235 Times Faster Than Your Hadoop Cluster." And his argument for this was a data set that had 4 gigabytes of RAM. Okay, so Bash might be faster with 100 gigabytes of RAM, but it won't be with 100 terabytes of RAM. There are HDFS clusters in production that have more than 600 petabytes of capacity. It is most likely that only Google has authored software that has produced clusters larger than that. I'm talking about single clusters, not clusters of clusters. You can happily support 60,000 concurrent operations on HDFS. Try that on your local hard drive. Multiple machines multiply your throughput. And even if you have a small data set, it can still be the most cost-effective solution. HDFS doesn't run just on disks. It also runs on RAM drives. It has the ability to move data back and forth automatically, so it can be extremely quick. If you look at why I would encourage you to look at distributed systems, is that single computers, even if you're buying a $50,000 box, there is always going to be some sort of hardware limitation side of it. Your SATA bus on any of your computers at home are most likely going to go up to 1.2 gigabytes per second. RAID has limits. Even if you did NVMe RAID, you get maybe at most 25 gigabytes a second. The PCIe bus that most of your graphics cards are plugged into can only hit up to 32 gigabytes per second at the 3.0 spec. RAM bandwidth on most machines, on those Intel chips that you have in your laptops, that's usually around 25 gigabytes a second. If you shell out for the really expensive Xeon chips, then you would get up to maybe 85 gigabytes per second, but that's tops. Distribution gives you the chance to combine of your disks. If I buy one hard drive and can do 100 megabytes a second, that's great. I'll buy 9 more. Now I can do 1,000 megabytes per second. The other piece around it is that when you store information on a disk, disks fail all the time. They have like a 2% failure rate per year, and it's probably even worse when you're running them all the time. With HDFS is you can set up rack awareness where you have multiple racks inside of a data center that don't share the same power or many other characteristics. And you can say, my data, I want to have one copy of it in this rack, make a second copy in another machine inside that rack, and then the third copy I want you to put to the other rack so that if you take out a single rack, you still have your data somewhere else in that data center. The other cool thing about it is with replication is it can be file specific. So you can replicate your popular files across all of your disks if you want to. So this gives you a chance to scale your storage, your compute, your RAM bandwidth, your SATA bus bandwidth, and your network throughput. This is something that it's actually quite rare to find in a lot of systems. How the cloud helps in this one? On Amazon, I'm sure you guys have all heard the sales pitch before, you can buy one machine for 10 hours, or you can buy 10 machines for 1 hour. It's the same price. And if you use spot instances, that can reduce the cost of the machine by 80%. So why not just rent 5 machines for the price of 1? And then you can distribute your throughput. If you have a system that can work across multiple machines, you can really benefit from that. Let's talk about how HDFS and Hadoop got started. I do apologize for intermixing these two terms a lot. HDFS software. So back in the 1990s, Doug Cutting and Mike Caffarella were working on a web crawler. The software that they were developing went through a lot of iterations, and the distributed file store that they built inside of it changed quite a bit when Google released the Google File System paper back in 2003. That basically inspired what is HDFS as we know today. Google has since gone on to deploy Colossus, which replaced the Google File System, but back then this was the cream of the crop. Shortly after they developed that, this got deployed at Yahoo. This was what they used for all their search technologies. 2006, Hadoop 010 got released as an open source project. And when we talk about Hadoop, there are 5 major elements to Hadoop. First is the Hadoop Distributed File System, HDFS. The second one is the resource negotiator. That's what's effectively distributing compute across your cluster. They have the MapReduce framework, which gave you some software to try to help you parallelize what you were building. It does have some purposes, though. Spark and a few other tools, and Presto have all built their own job schedulers and executors since then. There's a key management server, which is a core part of the encrypted at rest. So, if Edward Snowden comes into your data center and starts ripping out hard drives, he's ripping out nothing. When he tries to hand them over to a newspaper and they try to read off those drives, it's all encrypted. It's encrypted at rest, and that's quite crucial right there. The other key thing that they're building right now, it's not finished, is Apache Ozone. And what this will do, allow you to store trillions of files inside of a cheap cluster, and you'll have an Amazon S3 API. So you can use all your S3 tools just to read and write files off of there as another object store. It's currently in development. It's at version 0.4 at the moment. So it's a little ways off of getting to 1.0. So how files are stored in HDFS. HDFS will put up to one file in a single block. And by default, those blocks are 128 megabytes. So if you have a 256 megabyte file, it'll split it up into 2 blocks. Those blocks will then be distributed across the data nodes. So B1 is also here, and it's also here. B2 is here, here, and here. And it's among all the machines. It's a little bit like BitTorrent and how that they're orchestrated between one another. And there's a name node that keeps track of what files map to what blocks. And that's called your FS image. And that's quite an important thing in the Hadoop and HDFS space. So when you do change anything in your file system, if you edit a file, if you delete a file, if you add a file, they're recorded in an append-only edit log. And then there's a secondary name node that will take your file system image and your edit log and merge them together. This means that it's much more reliable for editing files and making sure you don't corrupt your system in the process. If you look at how like Postgres writes data to disk, it does a very similar thing. It's a very safe way of storing information. And HDFS does a good job of taking advantage of like memory mapping and cachings and whatnot. This is a very well optimized way of working with files on drives. So the size of files is actually quite interesting. Ideally, your files will be between 128 megabytes and 2 gigabytes. If they're less than that, you're going to start to have pressures on your FS image. So last week, I had a client that had a cluster that had 6 million files on it, and I had allocated 8 gigabytes of RAM to the name node, and the name node is complaining, this isn't enough RAM for me to keep track of 6 million files. I'm going into safe mode, and then I have to go and figure out how to give that thing more RAM. So ideally, you want to try to keep your files together. There is an upward limit of about 500 million files. If you have that many on a cluster, you probably have at least 192 gigs of RAM available just for the name node itself. And even there, like it's going to start to get hairy. So there are some cool techniques where you can use Kafka and Flume to group together small files together. So if you're microbatching, every 5 minutes you're creating a file of all the drives that are going on in Talend right now, and you start to produce like loads and loads of files every day, you can use Kafka and Flume actually to group them together so that you're creating fewer, larger files. And Presto and Hive can also do this. They can merge millions of files a minute, which is exactly what I did last week to sort of deal with that issue. There's a charity called Common Crawl. It's actually started by a few people at Google. They crawl the internet every month, and they store everything on files on S3. And Amazon actually let you retrieve those files free of charge. If you want to compute them on Amazon, you just have to pay for the EC2 instances. But they have over 4 petabytes of data on S3 that you can work with right now. And it's interesting how they've managed to merge. Web pages are small, yeah, they're like a few kilobytes if you get rid of all the JavaScript. And they made their files between 100 megabytes and 1 gigabyte each. If you Google for petabytes of websites, you'll find this link here. It's from my site on how you can actually work with that data. So if you have a few dollars, you can start working with petabytes of data using Hadoop on Amazon today, basically. All the instructions are right there. So the disks that you'd be using. The good thing about HDFS, if it looks like a disk to Linux, you can use it. It doesn't really matter. You can have SD cards, NVMe drives, hard drives, everything works. There's a storage policies piece that got released with Hadoop 3.1, and this allows you to automatically move data from between different storage devices. So if you can imagine, if you're using a RAM drive, your cost per gigabyte is huge there. You don't even want to keep a small amount of data in there. As soon as something's not popular, you'd want to maybe move it down to SSDs. If it wasn't popular there, you want to move down to hard drives and then to archival storage. This can all happen automatically with storage policies. So you can create a whole pipeline, as it were, of when you need your data and you need it to be fast, it can move up to the RAM drive. Otherwise, just move it down to the cheapest cost per gigabyte that you can possibly find. Other key thing is when I see a lot of customers, when they're trying to set this up, they try to set up RAID first. HDFS does not need RAID. RAID is an anti-pattern. You can completely forget it, which is great because it's usually pretty complicated to set up and get right in the first place. So just a dumb motherboard with a bunch of SATA drives plugged into it is really all that you need. Let's talk about replication. So when you have all these blocks, they're stored across your data nodes. The data nodes are always telling the name node, here's all the blocks I have, and here's a checksum of them. So the name node knows when a data has been corrupted on one of the systems, and it'll tell it to replicate from the other ones. If there's blocks that are missing that don't have enough replications, it can instruct the nodes to distribute them between each other. As I mentioned earlier, there's also rack awareness that you can set up so that no one rack in your data cluster holds all that data. So the interesting thing you can do with that is on EC2, maybe you want to allocate some M4 instances on one machine and some C5s on another. It's unlikely that Amazon keep those in the same cage. They're probably in different parts of the data center. So instead of having to distribute among different availability zones and getting all that network latency in the middle, you can simply just use a bunch of different EC2 instance types and create distribution within their data center within the same building. Amazon will probably not guarantee that that's the case, but Cloudera wrote a book in which they think that is how it's set up there. There's also another interesting thing is that anyone familiar with RAID or other replication techniques, often you need like 3x to get really good, reliable replication. HDFS supports erasure encoding, which only needs 1.5 times the space of the original file. I'm in the JIRAs for the Hadoop project, and there's people in there that have worked on S3 and worked on Azure blob storage. They've made comments to me which lead me to believe that S3 and your Azure blob storage use erasure coding as the replication method. So if that is the case, I'm getting what S3 already has right now on my own network. Just not all the other great things that Amazon built. So let's walk through an example of how this is useful. Imagine I have 500 gigabytes of uncompressed, yeah? And I want to replicate those 3x so that I don't lose them. If I write that out sequentially, I'll have 1,500 gigabytes worth of data. Now let's take those CSVs, let's convert them into a columnar storage using ORC, and each column will be compressed, say, with snappy compression, yeah? I've now taken that 500 gigabytes and I've turned it into 80 gigabytes. So if I replicate that out 3 times, I'm only using 240 gigabytes of space. Now let's, instead of using 3x replication, let's use erasure coding. So that 500 gigabytes is now turned into 120 gigabytes on disk. I'm now an order of magnitude less storage required to store that information. And if you think about the time associated with that, if I had to sequentially write out 1,500 gigabytes per second to each drive individually, saying my source drive can only do 100 megabytes a second, it would take 4 hours, yeah? But if I can make sure my source drives can actually keep up with it, and I can get, say, 300 megabytes per second storing across 3 different nodes, that brings it down to 7 minutes. HDFS clients. So there's a standard HDFS client. It's written in Java. It's JVM based. So you might think Hadoop isn't fast when every time you're executing a command, you're waiting 2 or 3 seconds until the command starts to execute. This is the JVM overhead, and it's quite sad. The server side, everything there, it's already running. It's already set up. It can actually respond very quickly, but the clients being written on the JVM is what gives people impression that it might not be that fast. There is another client called Go HDFS, and Go does not use the JVM, so everything's instant. It feels like it's a local file system all of a sudden. I've done benchmarks on my website. If you look for working with HDFS on there, you'll see the benchmarks I show, like Go HDFS just blows it out of the water in a lot of cases. There's also the file system fuse, so you can fuse a mount point to HDFS so it looks like a normal Unix folder on your computer, and you can just store data in it, and you're actually talking to HDFS. The guys at Spotify, they built Snakebite, which is Python-based. It's both a CLI tool and Python bindings that you can use inside your applications. And Apache Arrow has also created a C++-based HDFS client with Python bindings. The HDFS support that we're seeing in ClickHouse now from Yandex, that's actually using that C++ code there. So I'm going to talk about some of the downsides of HDFS. I got told to put these slides in here if I wanted to present tonight. First and most important, that FS image is a single point of failure. You really need to take care of it. You can set up multiple images and do serial roll-ups so that there's multiple copies and they have to all properly commit before anything goes ahead. HDFS is not metadata bound. It is bound purely by IO for the most part. So you want to make sure that's set up. The default settings is just to use one FS image, and that would be dangerous. You don't want to lose your data. And if that FS image is gone, good luck putting your data nodes, getting the blocks in your data nodes back in order. Small file overhead, you just can't start uploading like 16 kilobyte files like my client did last week. You need to have a strategy for how you're going to roll things up together. Ozone is not ready yet. I don't know when it's going to be ready. It looked ready 4 months ago, but it's not. There's a lot of Java going on. So for the server side stuff, it doesn't matter. You launch your server. It doesn't matter how long that takes. Once it's up, it's up. But the clients, if you're using JVM clients, you're going to wonder why things aren't as quick as they could be, especially when you lot. That's where you want to start to look for the non-JVM clients to see if they can help you out. The problem with that is a lot of the alternative clients are incomplete. So Snakebite can't upload to HDFS. Other clients, they can't append files. There's a lot of just, there is a reason to use like 5 different clients to get the best of everything. The other problem I found is certain features have questionable popularity. You might find issues and think that you're the first person on the planet to find it, which is very odd for software that's 15 years old. The community. So the software, it's also fairly heavy development in 2019. Like it does not stop. They have a very healthy community developing it, but like you think they'd be kind of finished by now, and they're not. And the other problem is HDFS itself. It lives with the rest of the Hadoop code base. So you see a million lines of Java, and most people just go running the other way. It's a real shame that the software just couldn't live in its own repo, and maybe even sort of look to port to other languages by now. The JVM was a great idea 20 years ago. I think there's a lot of languages today that would really help the software move forward, and especially find new developers to work on it. Outside the people at Cloudera and Hortonworks, the documentation for Hadoop is absolutely terrible. It's horrendous. People don't write blog posts about this, and when they do, it is an absolute mess 99% of the time. And I really hope that this does change. I started my blog because Hadoop help on the internet was awful. I think people from Cloudera went onto Stack Overflow and gave misleading answers to every single question to avoid having any competitors competing with them for work. It's the only answer I can give. If you go to Stack Overflow and you see Hadoop in a tag, don't read it. Go away, look somewhere else on the internet. Of the 171 contributors, most of them are at Cloudera, and they all make money consulting, selling training, selling certifications, supporting, and doing implementations. There is no financial incentive for them to publish great documentation. Even when they're paid to write a book, you can see that they're very much holding back. Expertise in HDFS and Hadoop in general is very expensive. I've been quoted $2,000 a day to have a consultant come into one of my clients' offices, and that seemed like a good price to me. Good books discussing HDFS, extremely rare. I saw like one book last year that was any good. And that's pretty sad for something that is deployed in a lot of different places. And the other key thing is, especially if you're trying to pitch this to a client, is AWS 3 is understood by like virtually every developer in the world. So you're going to be spending all your time explaining how both of these complement one another, how HDFS works with S3. When certain situations exist that S3 isn't the best answer, where HDFS can help. And there's times where HDFS isn't the best answer for a business as well too. So there's always going to be like an hour-long presentation on why do these two things exist and what should we be using. Other downsides of HDFS. Do you recognize that piece of paper there? That's UBS being sued in court by Parallel Irons for using HDFS. Parallel Iron claimed that they had a patent that was violated by HDFS, so they went and found some big HDFS users, and they filed lawsuits against them. Thank God people like Rackspace have actually filed actions against Parallel Iron, but this was a real annoyance for a long time. Companies are worried that, am I going to use this software and get sued? Or what's the deal? Like, were patents actually infringed or not? That did close. I don't know what the result of that was, but if it was the case that UBS had to pay out, we would definitely have known about it by now, because HDFS would be a thing of the past pretty quick. And this is actually a problem with a lot of open source software. So you do need to be mindful of the legalities of what you're using, that you don't get your clients in trouble. Other bits around operations. Adding nodes to an HDFS cluster could involve fewer steps, Funny enough, all of these cloud providers have their own managed offerings, which they make it really easy to add nodes. But if you want to do it by hand in the software, it's like 4 or 5 steps depending on what kind of node you're going to add. Upgrading is also a very involved process. They have a hilarious wiki article on how they think you might be able to do it, but it's absolutely inconclusive. Also, if you're running bare metal storage, you'll need to buy your drives ahead of time. And with that, there's the issue that the cool kids stopped buying metal drives a long time ago. They want to use Amazon for everything. Problem is that the cost per gigabyte per hour on EBS, it really needs to come down. It is quite expensive compared to bare metal. And almost with a lot of my bigger clients, it's a case of trying to balance what should we really be using for this particular case. We know S3 is going to cost us a fortune if we try to store a petabyte of data on there and leave it on there for the next 5 years versus just buying the drives and depreciating them. So that's another issue where, yeah, trying to find out what's best is also quite hard. Oracle's JDK license uncertainty. Every year I start hearing stuff out of Oracle about Java, and they're wanting to change licenses. They're trying to charge money. Who knows how long they'll have their developers working at OpenJDK. This is really annoying. I thought the Python 2.3 problem was annoying. This is even worse. Practically everything in the Apache projects is written in Java. Maybe like 10 projects I can think of that were written in like C++. That is really frustrating. I'm sure every Java developer knows about this. I don't know if they worry about it. It's sort of like Brexit, where we keep on putting it off, but it could come back to bite us at some point in time. So if you do want to set up HDFS, you can do it on a single machine. You do not need to go out and buy 500 hard drives. You can take your laptop, you can install Oracle's VirtualBox, or you can install VMware on it, and you can get it set up on there. If you go to the cloud, just going to need 2 instances, 8 gigabytes of RAM. No need to pay the EMR tax. Or you can get a DigitalOcean droplet if you don't like Amazon. Or you can just get an old PC with 8 gigs of RAM on it running Ubuntu 16. If you search for install Hadoop 3 single node into Google, my site should be in one of the top 5 results on there. So you can get this running in like an hour or so on your machine at home. If you want to do a cluster, EMR, Dataproc, HD Insight, they all will launch with HDFS. It's right there. So if you're willing to hand over a bit of money, or if you have credits, they often give credits to people who are just trying things out, like 750 hours free sort of thing. So you can find ways of doing this for free on the cloud if you know the right people to ask. And when you do get those launched, you'll notice here, this is the HDFS command. It happily works with S3. It works with Google Cloud Storage. It works with Azure Blob Storage. So it might seem odd, like, okay, which backend am I using? But they're all happily supported. That there is a picture of 3 Raspberry Pis and a fan pointed at them to keep them cold. 2 of them have SD cards plugged in, and 1 has a hard drive plugged in with a USB mount on it. And that cluster is documented in this blog post that I have put up there. So if you only want to spend like 100 euros on your cluster and you want to use a lot of used kits, the fan is actually 20 euros. So 120. It is quite possible. And you know, from there, you've learned about 50% of what you'd need to go work in an investment bank and take care of their HDFS stuff. So it's not like there's this giant leap. It's just get it installed and try. With that, I do want to thank you. But before, I want to ask you guys to do something. If you guys could go to that URL, there's like a 10-question survey. I think it's 10 questions. I looked at it before this started. They just want to get some feedback on these talks. So you probably want to go to careers.bolt.eu as well too. I don't work for Bolt and I'm not a recruiter, but they want to hire people. So if you're unemployed, you should get a job today. Okay, with that, I'll open it up for questions. Okay.
Thanks for the great talk. You mentioned that describing the difference between S3 and HDFS is an hour, but can you give me a 30-second summary?
So S3, let's say S3 versus EBS, yeah? We're going to be all Amazon on this one. EBS, you're going to spend twice as much money per gigabyte per hour to store your data, but it's going to be twice as fast than S3. Your durability, well, it's as good as that cluster is, versus S3 has 11 nines of durability. So is this the master copy of your data, or is this just a derivative that you're just trying to do some analysis on? Does that answer your question? Yeah. Okay. Next one. Okay. Oh, all the way at the other side.
What do you think is the future of the on-premises solutions of HDFS, and or compared to clouds? Will the cloud vendors slowly die out to 98%?
Every on-premises customer that I deal with, they have reasons for being on-prem that they can't really fight against. It's upper management that put those rules in place, or there's laws in their country that stop that data from leaving their premises. So on-prem isn't going anywhere. It won't disappear. It's usually more expensive because you have people that have to deal with stuff. You're dealing with broken things. Amazon subsidizes every single one of their customers' businesses because they are effectively doing this at scale, and they're doing it on behalf of everyone else. So I'm not dealing with broken drives on Amazon ever. So they won't. The cloud won't disappear, and nor will on-prem. Here's what I think will happen. At some point, it's going to be like 70 or 80% cloud, 20% on bare metal in 10 years' time. In terms of what will the on-prem look like, there's a lot of databases that are adding HDFS support. If you go download any sort of new database right now, go look at all the libraries they include. It's loads of Hadoop-based libraries that are in there. They're really converging on that. You don't want to have to convert your data between 15 different formats, and you don't have to make yet another copy of your data every time you try a new database. You just want to see the execution work. There's no reason for any database to recreate what HDFS has already created, because most of the times they won't improve on it, or they'll get one or two features right. But beyond that, HDFS has so many features, I really couldn't cover them in a talk. Next question.
Yeah, thanks for that. Really interesting. So I work with Elasticsearch a lot, and well, first of all, I was really interested in the first table you showed, where it came dead last in the ranking and failed to run the last query. So I was curious as to what kind of query that was, and I was also curious as to how does HDFS relate to, or how is it different to Elasticsearch, or are they even in the same kind of ballpark?
It's not really comparing apples to apples with them. To answer your question on that, the fourth query was doing an aggregation where it's also modifying the results. And in that very old version of Elasticsearch, it wasn't supported. I'm sure it's fine now. It's actually not dead last as well too. I found a way of getting SQLite to work with Parquet files on HDFS. That was actually the slowest benchmark I've ever run. And the only reason that's the slowest is if I imported this data into Postgres and I queried it there, that would come dead last. Row-orientated storage is not good for analytics. It's good for transactions, for knowing in the moment, for making sure you have a perfect copy of your data. But when you're trying to do analysis, that's why these other tools come in here. That's why SQL Server, Postgres, MySQL, they'll never disappear. Elasticsearch, for example, it's an inverted index. Ultimately, what it's really good for is doing searches that virtually every other piece of software would have really struggled to provide. You have a mini Google in that piece of software. It's fantastic. And if you look at how Elasticsearch was built, underlying engine is Solr. Who built Solr? Same dude that built HDFS. That's all the same lineage of software. So obviously today Elasticsearch is a public company. They've done a lot of things to their software. That benchmark does need an update. It's not respectful of where Elasticsearch has come today, and nor is it respectful of where Redshift has come in the last couple of years as well too. So as I get time, I do try to update those benchmarks every year or two, just to try to show that things are progressing. Is there another question?